Every supply chain in the world is caught in a permanent tug of war. On one side, pressure to hoard material to prevent catastrophic shortages. On the other, the financial drag of storing goods you don't immediately need. Standing inventory is frozen capital. The longer a product sits in a warehouse, the more it degrades profitability through storage fees, insurance, risk of obsolescence, and the opportunity cost of tied-up cash. This is the holding cost. Letting your warehouse run dry triggers a stockout cost. You lose the immediate sale, damage customer trust, and risk long-term reputational hits. To navigate this tension, logistics engineers have shifted their approach. We're going to look at how inventory management evolved from the rigid, static formulas of the 20th century into the probabilistic, AI-driven networks running global trade. Profitability requires finding the intersection where the cost of holding goods and the risk of running out cancel each other out. For decades, the baseline tool for finding that balance has been the economic order quantity, or EOQ. It solves for two competing forces. Buying in massive bulk drives holding costs up because goods sit longer. Placing frequent small orders keeps inventory low, but causes ordering costs, the administrative and transport fees for every shipment, to skyrocket. This graph shows how those variables interact. The upward curve is holding cost. The downward slope is ordering cost. The U-shaped line above them tracks the combined total. The EOQ is the exact lowest point on that total cost curve. The model requires a perfectly deterministic world to function. It assumes consumer demand drains at a constant known rate and that supplier shipments arrive with a completely static lead time. In a vacuum, EOQ calculates the absolute cheapest way to run a warehouse. In practice, it remains an intellectual baseline rather than a reflection of how the real market behaves. PT Toroco Jaya is a specialty coffee processor that historically relied on manual, irregular ordering, buying beans about 9 times a year. To optimize this, we map their operational variables: an annual demand of 2,000 kilograms, a fixed ordering cost of $50 per shipment, and an annual holding cost of 50 cents per kilogram. We plug those into the EOQ formula. The math dictates an optimal order size of roughly 632 kilograms. Under this new policy, ordering drops to 4 times a year, driving total annual inventory costs down to an optimized $316. They also need a reorder point. Based on their daily usage and a strict 10-day supplier lead time, a new order triggers when the warehouse stock drops to 55 kilograms. This structure provides massive financial efficiency, provided that 10-day lead time and the daily consumption rate never deviate. Supply chains are chaotic. A single storm delays a shipment, or a viral trend clears a shelf in an hour. When that happens, the clean, static assumptions of EOQ break down into chaotic spikes and shortages. Engineers build safety stock, a calculated probabilistic buffer designed to absorb this variance. This buffer is calculated using a normal distribution to define a service-level z-score, the probability of avoiding a stockout. Pushing that target from 95 to 99.9% requires an exponential leap in safety stock, causing holding costs to skyrocket. Pursuing a flawless 100% availability rate across every item in a catalog will mathematically bankrupt an organization through excess capital holding costs. A true safety stock calculation accounts for the volatility of downstream customer demand and the unpredictability of upstream supplier lead times simultaneously. This comprehensive statistical derivation isolates that dual volatility. The equation's left side captures consumer variance, average lead time multiplied by demand standard deviation squared. The right side isolates supplier variance, average demand against lead time standard deviation. You take the square root of that combined variance and multiply it by your chosen z-score to find the exact number of physical units required to pad your inventory. This formula allows supply chain engineers to mathematically defend their networks against external chaos without relying on guesswork. Because maintaining high z-scores is expensive, engineers cannot protect all inventory equally. They strategically allocate capital using an ABC XYZ matrix. This ABC XYZ matrix segments products. The vertical axis measures financial impact, while the horizontal axis tracks demand volatility. A predictable AX item requires minimal safety stock. Conversely, an erratic, high-value AZ item demands intensive oversight and massive capital buffers to prevent stockouts. Even this matrix relies on historical forecasting. To shift toward a demand-driven model, modern supply chains utilize deep reinforcement learning and IoT sensors. These AI systems ingest real-time external variables, everything from macroeconomic indicators and weather patterns to social media sentiment. AI systems autonomously recalculate the standard deviations and optimal order limits in real time, executing adjustments before a human operator registers a shift in the market. When you combine these optimized strategies, the final test of network performance is the perfect order, often measured as on time in full. A perfect order requires 5 simultaneous operational successes. The shipment must be delivered on time, in the full quantity requested, free of transit damage, with accurate fulfillment and accurate invoicing. From the customer's perspective, satisfaction is strictly cumulative probability, not an average of these steps. Take a company scoring between 94 and 99% across all 5 individual metrics. Multiplying those high individual probabilities together reduces the actual perfect order rate to just 84%. Minor, isolated friction points compound rapidly into systemic service failure. A 1% error in packing and a 3% error in routing combine to degrade the end-user experience. Achieving systemic reliability requires looking past isolated performance indicators and optimizing every link in the mathematical chain. We've moved from the rigid formulas of the economic order quantity to the fluid, AI-driven architectures required to navigate global trade. Mastering this discipline demands constantly balancing the exponential costs of holding capital against the compounding risks of operational failure. Inventory management is the rigorous integration of probability and technology, absorbing market volatility long before the customer feels it.